The weight of looking up. The air is a little thinner at this hour. Not literally, the atmosphere does not change its composition because it is late. But something about the way the body settles when it is tired makes the world feel less pressurized, less insistent, and the sky, if you happen to be somewhere you can actually see it, seems to come down a little closer. Not friendlier, just closer. There is something your eyes do when you look at a star. They go slack. The focusing muscles that have been working all day, adjusting for screens, for faces, for the distance between you and whatever needed your attention, they release, because a star is functionally at infinity, and infinity requires nothing of the human lens. The eye that looks at a star is the most relaxed the eye ever gets, and the brain briefly has nothing to calculate. The star is just there, in the dark, and your eye is just open, and for a moment the whole apparatus of vision is running at its lowest possible load. That feeling is real. It is not a metaphor. Most of what you see when you look at the night sky is old. Not old in the way antiques are old, or old in the way your grandparents are old, but old in the way that makes every other kind of old feel like it happened this afternoon. The light arriving at your eye from the Andromeda Galaxy left its source 2.5 million years ago, which means it has been travelling since before the genus Homo existed, since before the ice ages that shaped the landscape you live in, since before anything that would recognise itself as human took a single breath. It has been crossing the dark for all of that time, and it just now arrived. At your eye. At this hour. There is a word for the study of where things are in the sky and how they move, astrometry. And there is another word for the study of how those things are distributed across the universe at large-scale structure cosmology. And both of these fields have been quietly producing results for decades that do not quite fit the picture most people carry around when they think about the universe. The picture most people carry is of something roughly even, roughly the same in all directions, a vast, more or less uniform distribution of galaxies and clusters and empty space, expanding outward from a point, spreading in every direction at roughly the same rate, with no particular preference for any one direction over any other. That picture is wrong. Not a little wrong. Wrong in a specific way that has a specific shape, and that shape has been there quietly for 4 billion years, and nobody looking at the night sky with the naked eye has any way of knowing it from the looking. Here is the thing about the sky as most people understand it. It feels complete. You look up and there is a lot there. More than you can count, more than you can name, more than you can fully take in, and the abundance of it tends to give the impression that the sky is full, that it is a kind of fullness, an excess, a surfeit of things. It is not full, it is mostly empty, in proportions that are hard to hold in the mind even when you know the numbers. The observable universe is something like 93 billion light-years in diameter. The matter in it, all of it, every star and planet and gas cloud and dark matter halo, occupies a fraction of that volume so small that if you scale the observable universe down to the size of the Earth, all the matter in it would fit in a space smaller than a grain of sand. The rest is void. The rest is, in a very literal sense, nothing. And yet the nothing is not even. The voids are not randomly distributed. The matter is not randomly distributed. There is structure to the distribution, filaments, sheets, clusters, nodes, and that structure has a shape, and the shape has a direction, and the direction has been the same direction for longer than the Earth has been a planet. You are lying somewhere probably, or sitting in the particular way people sit when they're not quite awake and not quite asleep, when the body has gone ahead and started the shutting down process without quite getting permission. The position you are in right now, whatever it is the result of gravity. Gravity pulled you down to whatever surface is supporting you. Gravity is the reason the surface is there, the reason the planet is there, the reason the solar system organized itself the way it did. Every arrangement of matter you have ever interacted with is the result of gravity doing what gravity does, which is pull things toward each other, incrementally, patiently, over whatever time is available. Now extend that outward. Not just to the solar system, not just to the galaxy, out to scales where individual galaxies are the basic unit of matter, the way atoms are the basic unit of chemistry. At that scale, gravity is still doing what it does, pulling things toward each other, incrementally, patiently, and over 4 billion years of incremental patient pulling, the matter in the observable universe is not just clumped into galaxies. It has organized those galaxies into something that has a preferred direction, a large-scale flow. The sky is not full. The sky has been emptying in one direction for longer than life has existed on this planet. And the direction it has been emptying toward is something we've only recently been able to point at, and only imprecisely, and we cannot see it directly, and even its name, the Great Attractor, is borrowed from the feeling of not quite knowing what you are pointing at, but knowing that whatever it is, it has been pulling for a very long time. There is a thing that happens when a discovery is made in cosmology that is too large for the existing vocabulary to handle. The word that gets invented is usually too small for the thing it describes. The Great Attractor is a gravitational anomaly, a region of space with far more mass than the surrounding regions, toward which hundreds of thousands of galaxies, including our own, are flowing at speeds that add hundreds of kilometers per second to the velocities those galaxies already have from the expansion of space. The flow is called the bulk flow. The region they're flowing toward is partially hidden behind the dense disk of the Milky Way, behind what astronomers call the zone of avoidance, which is a name that sounds like caution, but is really just a description of the problem. There is so much intervening dust and gas along the plane of our own galaxy that we cannot see clearly through it to the structures on the other side. The Great Attractor is on the other side. We know it is there because of how things move around it, the way you can know something is in a room by watching how people in the room orient their bodies. The galaxies are oriented. They have been oriented for a very long time. Look up if you can, or just picture the sky. Picture the flat, undifferentiated darkness with its points of light, the way it has looked to every human who has ever been outside at night, the way it looked to people who had no context for what the lights were, and the way it looks now even to people who do. The flatness of it, the evenness of it, the impression it gives of balance and completeness and a kind of cosmic democracy where every direction is as good as every other. That impression is the thing this video's about, and the impression is wrong, and the way it is wrong is so large and so old and so thoroughly built into the structure of everything around you that you have been inside it your entire life without any sensation of tilt. There is no sensation of tilt. That is the thing. The lean is not something you can feel. It is not something any instrument on Earth can detect directly. It is visible only in the aggregate behavior of hundreds of thousands of galaxies moving through space over billions of years, each one contributing a small component of velocity in a particular direction, and all those small components adding up, over time, into something that has a shape and a destination and an origin that we have not fully located. The sky looks still. It is not still. It has been moving in one direction since before there was a sky to move. And the direction is something you have to come to slowly. It does not arrive well if it is handed over too quickly. There are a few things that need to settle first. One direction. The universe is expanding. You have heard this. Most people have heard this at some point in some form, and have filed it under things that are true and large and not immediately relevant to anything. The universe is expanding. Fine. In every direction, at every point, space itself is stretching, carrying galaxies away from each other the way dots on a balloon move apart when you inflate it. No center, no edge, just more distance, everywhere, all the time. That is the standard picture. It is accurate. It is also incomplete in a way that took decades to fully admit. The incompleteness is this. Not everything is moving only with the expansion. Some things are moving faster, or slower, or at an angle to what the expansion alone would predict. And when you map those deviations, when you subtract out the expansion and look at what is left, the residual motion, the velocity that cannot be explained by space simply getting bigger, you find something that is not random. You find a pattern, a coherence, a large number of galaxies spread across an enormous volume of space, all carrying a component of motion in roughly the same direction. This is called peculiar velocity. The word peculiar here does not mean strange in the way it sounds. It means particular, individual. The velocity that belongs to a galaxy above and beyond what the expansion gives it. And peculiar velocities, when you look at them across large enough scales, do not point in random directions. They lean. They have been leaning for a very long time. In the mid-1980s, a group of 7 astronomers, they became known informally as the 7 Samurai, which is the kind of name that gets invented when a group of people are doing something that makes other people uncomfortable, began measuring the distances and velocities of elliptical galaxies across a large region of sky. Distance measurement in cosmology is layered, imprecise, dependent on a chain of calibrations that each carry their own uncertainties. But the 7 Samurai were careful, and their results were consistent, and what they found was that the galaxies they were measuring were not where the expansion alone would put them. They were displaced, moving as a group towards something. That phrase sat badly with the community for a while. The universe was not supposed to have a something that things move toward. The universe was supposed to be, at large enough scales, roughly uniform, homogeneous, isotropic, the same in all directions. These are not just aesthetic preferences. They are foundational assumptions built into the standard model of cosmology, and results that challenged them were not dismissed exactly. But they were held at a careful distance while the community waited for confirmation or refutation. The confirmation came, slowly, from multiple independent groups using different methods and different galaxy samples. The signal was real. The flow was real. Here is what the data looked like, stripped of its technical language. Imagine you are watching a river from above. You can see the surface moving. You can measure the speed at different points, and if you look carefully enough, past the local eddies and currents, past the places where rocks and bends create their own small motions, you can see that everything is moving in the same general direction, some faster, some slower, some at slight angles. But the net direction is clear. There is a downstream. The observable universe has a downstream, roughly speaking. The flow is not precise. It is not a river. It is a broad, volumetric drift across hundreds of millions of light years, a statistical tendency rather than a clean current, and the center of that tendency, the point everything seems to be drifting toward, is not a point at all but a region, and the region is large, and it is partially obscured, and it contains things we've not fully catalogued, and even the best current models of what is causing it are probably not the last word. But the flow is real, the direction is real, and it has been real for long enough that the word direction, applied to the universe at this scale, stops feeling like a metaphor and starts feeling like a measurement. There is a number worth sitting with. The Milky Way, our galaxy, is moving toward the general region of the Great Attractor at roughly 600 kilometers per second relative to the cosmic microwave background. The faint afterglow of the early universe that fills all of space and provides the closest thing cosmology has to a fixed reference frame. 600 kilometers per second. That is about 2.2 million kilometers per hour. The Earth orbits the Sun at about 107,000 kilometers per hour. So the drift toward the Great Attractor is roughly 20 times faster than the speed of Earth's orbit, and yet you feel none of it, have never felt any of it, and would have no way of knowing it was happening without the kind of careful, painstaking, decades-long measurement that the Seven Samurai and everyone who came after them spent their careers doing. The universe is not required to be perceptible. This is something that takes a while to really absorb. The universe is under no obligation to make itself legible to the organisms living inside one of its smaller galaxies, and so it goes about its business. Its 4 billion year, 600 kilometer per second, continent-sized gravitational anomaly business, without any of it registering in your body, in your senses, in the particular slice of reality that your nervous system was built to navigate. You're on a planet, inside a solar system, inside a galaxy, inside a supercluster, and the supercluster has been falling towards something for 4 billion years, and the falling is silent and invisible and constant, and tonight is not different from any other night in that respect. What makes the large-scale flow strange, stranger than it first appears, is that the cause of it has to be enormous. Not enormous the way a mountain is enormous, or even the way a galaxy is enormous. Enormous in a way that requires you to hold several orders of magnitude in your head simultaneously, and let them multiply against each other until the number they produce stops feeling like a number and starts feeling like a posture. A region of space whose gravitational influence can accelerate hundreds of thousands of galaxies across hundreds of millions of light years has to contain, or represent, a genuinely extraordinary concentration of mass. The Great Attractor is estimated to sit around 250 million light years away. The mass required to produce the observed flow is on the order of tens of thousands of times the mass of the Milky Way. And the Great Attractor is not the whole story. It is itself embedded in a larger structure, the Laniakea Supercluster, and Laniakea is embedded in larger flows still, and those flows point towards something called the Shapley concentration, which is one of the largest known concentrations of mass in the observable universe, and even the Shapley concentration may not be the last word. The chain does not resolve cleanly. That is worth knowing now. One direction. The phrase is almost too simple for what it describes. It is not one direction in the way that a compass needle points in one direction, precise and unwavering and correctable if it drifts. It is one direction in the way that a very large body of water, seen from a very high altitude, appears to be moving in one direction. A tendency, a bias, a statistical lean that only becomes visible when you zoom out far enough that the individual exceptions stop mattering. Zoom out far enough. That is always the instruction with cosmology. Zoom out until the Milky Way is a point. Zoom out until the local group, the Milky Way and Andromeda, and 50 or so smaller galaxies that form our gravitational neighbourhood, is a point. Zoom out until the Virgo Supercluster, which contains the local group, is a point. Zoom out until Laniakea, which contains the Virgo Supercluster, is a point. And then look at how that point is moving relative to everything else. It is moving. It has been moving for 4 billion years. The direction has not changed. The thing that makes this hard to hold is not the scale. People are reasonably good at accepting that cosmological scales are beyond intuition. The thing that makes it hard is the implication that the universe, at its largest observable scales, is not as symmetrical as it looks. That there is something that could be called, without too much poetic license, a shape to the distribution of everything, a grain, a direction the wood runs. The universe was not supposed to have a grain. The standard cosmological principle, the assumption that the universe looks the same in all directions at large enough scales, is one of the foundational ideas that makes the math of cosmology tractable. And the large-scale flow does not exactly violate that principle. The universe is still roughly homogeneous and isotropic at the very largest scales. Roughly, the flow exists within a framework that is, in the big picture, still fairly even, but roughly is doing a lot of work in that sentence, and the flow is real, and it has a direction, and the direction has been the same for 4 billion years. Something in the count is off. It has been off for a long time. The astronomers who noticed it first were not wrong to feel, alongside the data, a quiet and specific unease. The kind that arrives not when something is clearly broken, but when something that should be symmetrical just isn't quite, and you cannot yet say why. What a void feels like from the inside. You're already inside one, not a dramatic one, not one of the great voids that cosmologists name and catalogue and argue about at conferences. Just a quieter version of the same thing, a region of space that is underdense relative to the average, a place where the matter went somewhere else and did not come back, and what is left is not nothing, but is close enough to nothing that the distinction requires instruments to detect. The local void. That is its name. It sits adjacent to the local group, the small cluster of galaxies that contains the Milky Way, and it extends for something like 150 million light-years in the direction away from the Virgo Supercluster. We're not in the deepest part of it. We're near an edge, but we are in it, and we have been in it for as long as there has been a we. Empty space is not empty the way a room is empty when the furniture has been moved out. A room without furniture still has air, still has light coming through the windows, still has the faint presence of everything that used to be there registered in the dust patterns on the floor. Cosmic voids have none of that residue. The galaxies that might have formed there did not form there, or formed and migrated out, pulled by the gravitational attraction of the denser regions surrounding the void on all sides. What remains is a volume of space so underdense that the word underdense feels like it is trying too hard to be technical about something that is really just an almost empty, almost nothing, for 150 million light-years in one direction almost. Here is what is strange about being inside a void, from a physics standpoint. The void pushes, not the way pressure pushes, not the way wind pushes, but in a specific gravitational sense. Because the void contains less matter than the region surrounding it, the net gravitational pull from the void's interior is weaker than the pull from outside. The surrounding denser regions pull harder than the void's interior pulls back. The result is that anything inside the void, any galaxy, any cluster, experiences a net force directed outward, toward the denser walls of the void. Voids are not passive absences, they are active expellers. They push their contents toward the filaments and sheets and nodes that surround them, and in doing so they help build the cosmic web, the large-scale structure of the universe, the filamentary architecture that looks, in the maps astronomers make of it, like foam, or like the inside of a sponge, or like something you might find under a microscope in a biology lab. The void is making the structure. By being empty, it is building the walls. Stand in the middle of a field at night, far from any city. The darkness around you is roughly uniform. You cannot tell, just from standing there, whether the darkness extends for a mile, or for 100 miles, or for 1,000. The darkness does not announce its depth. It just sits there, indifferently, being dark. A cosmic void is like that, except scaled up by a factor that makes the comparison almost useless, and with the additional quality that the darkness is not just an absence of light, but an absence of the things that would produce light, and the things that would produce the things that would produce light, going down several levels of causal chain until you reach a place where the ordinary sequence of cosmic events, gas collapses, star forms, star lives and dies, gas disperses, star forms again, simply did not happen in the usual way or did not happen at all. The void is not a place where something went wrong. It is a place where the ordinary process of structure formation went right, just in the opposite direction. Structure formation is not only about where things accumulated, it is equally about where things did not accumulate. The void is not the background against which the story happens. The void is half the story. There are voids with names. The Botas void, discovered in 1981, is roughly 330 million light-years across, a region so unexpectedly empty that when Robert Kirshner and his colleagues first mapped it, one of them reportedly said that if the Milky Way had been in the centre of the Botas void, we would not have known of the existence of any other galaxy until the 1960s. The void contains very few galaxies relative to its size. The ones that are there are not randomly distributed, but tend to cluster along filaments even within the void, which suggests that even the emptiest regions of the universe are not completely free of structure, just very, very sparse. The KBC void, named for Keenan, Barger, and Cowie, who characterized it in 2013, may contain our own local group near its edge. It is estimated to be roughly 2 billion light-years across, which would make it one of the largest known underdense regions in the observable universe. Some researchers have proposed that living inside the KBC void could help explain certain tensions in cosmological measurements, discrepancies in the measured expansion rate of the universe that have been troubling the field for years. The void, in this proposal, is not just a background feature. It is an active ingredient in the numbers we measure, and therefore in the conclusions we draw, and therefore in how we understand the universe at its largest scales. We might be inside the explanation. That thought goes somewhere strange if you follow it. What a void feels like from the inside is nothing. That is the honest answer. There is no feeling. No sensation of emptiness, no awareness of being in a region of below average density, no proprioceptive signal that the matter is sparser here than elsewhere. The void does not announce itself. It cannot. There is nothing in it to carry an announcement. But there is a subtler sense in which being inside a void is not nothing. The void shapes the flow. The void is part of why the galaxies around us are moving the way they are moving, part of why the large-scale drift exists, part of why the peculiar velocities point in the directions they point. The void is pushing in its quiet gravitational way from behind. The denser regions are pulling from ahead, and the result of that push and pull, accumulated over billions of years, is the flow that the seven samurai measured, and that everyone who came after them confirmed, and that points toward the great Attractor and beyond. The void is not separate from the story of where everything is going. It is part of the mechanism that is sending everything there. 150 million light-years of almost nothing, and we are near the edge of it. And we have been near the edge of it since before the first complex life appeared on this planet, and we did not know it until very recently. And knowing it does not change anything about the day-to-day experience of existing on a small rocky planet orbiting an ordinary star. But it changes something about the shape of the context. The universe is not a uniform field with galaxies scattered through it like raisins in bread. It is a structure of absences and presences in dynamic relationship, and we are inside one of the absences near the edge, being gently pushed toward the presence on the other side, and the pushing has been happening for longer than there has been anything alive to be pushed. The void is where we live. The void is, in some sense, what we came from, the underdense region whose geometry helped direct the flow that brought matter to the places where matter accumulated enough to form what eventually became this. That thought does not fully finish. The pull that has no name. The paper had been sitting on desks for a while before anyone quite knew what to do with it. It was 1988. The Seven Samurai, Donald Lyndon Bell, Sandra Faber, David Burstein, Roger Davies, Alan Dressler, Roberto Terlevich, Gary Wegner, had published their analysis of the velocities of elliptical galaxies, and the result was sitting there in the literature like a stone in a shoe. Real, undeniable, and deeply uncomfortable. The galaxies were moving, not just with the expansion of space, toward something, toward a region in the direction of the Centaurus constellation, beyond the zone of avoidance, at a distance that the data could only bracket, not pin down. Something was there. Something with enough mass to be pulling hundreds of thousands of galaxies at speeds that added up across the sample to a coherent flow. The pull had no name yet. It would get one, eventually. But names come after understanding, and understanding was not yet available. What the data felt like, and this is a strange thing to say about data, but it is the right thing to say, was a confession. Not a clean result that slotted neatly into existing theory. A confession that something had been missed, that the universe contained a feature of sufficient size and mass that its absence from the standard picture was not a gap but a wound. The models that predicted how galaxies should move did not predict this. The models that described the large-scale structure of the universe didn't have room for something this big, this nearby, pulling this hard, nearby. 250 million light-years is nearby, in cosmological terms. The observable universe is 93 billion light-years across. 250 million is a fraction of that, so small it barely registers on a map. the Great Attractor, whatever it was in our cosmological backyard, and the models had not seen it coming. There is a particular kind of scientific discomfort that is different from the discomfort of being wrong. Being wrong is uncomfortable but clean. You were wrong, here is the correct answer. Update your model and move on. The discomfort the Seven Samurais result produced was murkier than that. It was the discomfort of a result that might be right, that the data supported, that multiple independent lines of evidence were beginning to corroborate, but that had implications nobody was quite ready to follow all the way to the end. The implication being, the universe is lumpier than we thought, lumpier than the standard model predicted, lumpier in a specific direction, and whatever is causing that lumpiness is large enough that we should have noticed it before, and we did not. Which means our maps of the universe have a hole in them in a place we were looking directly at and seeing wrong. That kind of wrong is slower to absorb. It requires not just updating a model, but questioning the instruments and assumptions and prior observations that led to the model in the first place. It requires a kind of epistemic vertigo that scientists are not, by training, well equipped to describe. The name came in 1988, in a paper by Faber and Burstein. They called it the Great Attractor. The name was provisional, descriptive, almost embarrassed in its lack of specificity, a way of pointing at something without claiming to know what you were pointing at. The Great Attractor. Not a named object, not a catalogued structure, not something that had been observed directly, but a gravitational inference. A thing that had to be there because of how everything around it was behaving. Like knowing there is a drain in a bathtub because the water is moving toward a point, without being able to see the drain itself. The drain, in this case, was behind the Milky Way, the plane of our own galaxy, thick with dust and gas and stars, all of it blocking the view, sat directly between us and the region where the Great Attractor appeared to be concentrated. This is the zone of avoidance, the band of sky where the galactic disk makes optical observation extremely difficult. The Great Attractor was in the zone of avoidance. Of course it was. There is something almost narratively unfair about this. The largest gravitational feature in our cosmological neighbourhood, the thing toward which everything in our supercluster has been flowing for billions of years, sits in the one region of sky that is hardest for us to see through. The universe hid the answer behind our own galaxy. Later surveys using radio waves and X-rays and infrared observations that can penetrate the galactic disk more effectively than visible light began to reveal what was there. The Norma cluster, Able 3627, a dense concentration of galaxies in the vicinity of the Great Attractor, with a total mass large enough to begin accounting for, though not fully explaining, the observed flow. The Great Attractor resolved partially into something that could be pointed at on a map. A real place, a real concentration. Not a mystery object, but a very large, very dense cluster of galaxies sitting at the intersection of several major filaments of the cosmic web. And then, and this is the part that the name Great Attractor does not prepare you for, it turned out that the Great Attractor was itself moving, not stationary at the centre of the flow, not the fixed point toward which everything else was falling, moving, falling, along with everything else, towards something further away, the Shapley concentration, discovered by Harlow Shapley in 1930, not understood in terms of its gravitational significance until much later. A massive supercluster of galaxies roughly 650 million light-years away, containing more than 24 galaxy clusters with a total mass that makes the Great Attractor look, in comparison, like a footnote. The Shapley concentration is now understood to be a significant contributor to the bulk flow, possibly more significant than the great attractor itself, depending on which analysis you trust and which dataset you use. So the chain is, we fall toward the great attractor. The great attractor falls toward the Shapley concentration. Everything in this corner of the observable universe is participating in a flow that is not caused by one thing, but by a hierarchy of things, each one larger and further away than the last, nested inside each other like a set of gravitational instructions passed down through scales we barely have names for. And whether the Shapley concentration is the last word, whether there is something beyond it that is pulling the whole assembly further still, is a question that the data does not yet cleanly answer. Some analyses suggest there might be. Some suggest the Shapley concentration is sufficient to account for the observed flow. The field is still, in certain respects, mid-argument. What I find difficult, and I want to say this carefully because it is not a scientific claim, just an honest report of what it feels like to try to think about this, is the sense of recursion in it. The pull that is pulling you is being pulled. The attractor is attracted. The thing you are falling toward is itself falling. And the thing that thing is falling toward may also be falling, and the chain may or may not terminate at something that is genuinely stationary in the relevant sense, and we do not have the observational reach yet to say for certain. The universe is a set of falls, nested inside each other. Some of them are very large and very slow and have been happening for 4 billion years. Some of them we can measure, some of them we are still finding the edges of, and somewhere in the structure of all those nested falls is the specific fall that contains this galaxy, and this solar system, and this planet, and you, lying somewhere in the dark, in a void, being very gently and completely imperceptibly pulled towards something we named, without fully knowing what it was. The name was always a placeholder. It still is, a little. Gravity at the wrong scale. Right now, your body is being held down, not forcefully, not dramatically, just the ordinary, constant, completely ignorable fact of weight, the pressure of your body against whatever surface is supporting it, the resistance that keeps you from floating off, the pull that made you tired earlier, and that is now, probably, winning. Gravity. The most familiar force in your life. The one you have been negotiating with since the first time you tried to stand up. The one that has never once let you go. It is also, in a strange and somewhat unsettling way, the weakest of the 4 fundamental forces. Electromagnetism is vastly stronger. The strong and weak nuclear forces operate at ranges so short they barely exist at human scales, but within those ranges they are far more powerful than gravity. A small magnet can lift a paperclip against the gravitational pull of an entire planet. Gravity is not strong. Gravity just has infinite range, and it is always attractive, and it never cancels out, and so given enough time and enough mass, it accumulates into something that nothing else can match, given enough time. That phrase is doing everything. 2 bodies with mass attract each other. This is the thing you learned in school, probably, the basic fact of gravity, and it applies everywhere from 2 dust particles drifting in interstellar space to 2 neutron stars spiraling toward each other at a fraction of the speed of light. The formula is the same, the constant is the same, the geometry of the force is the same. It falls off with the square of the distance, always, without exception, at every scale. The law does not know you are using it at the scale of galaxies rather than apples. It just applies. But at the scale of galaxies, what the law produces is different in character from what it produces at the scale of apples. Not because the law changes, but because the time available for it to operate is so much longer. An apple falls from a tree in a fraction of a second. A galaxy falls toward a gravitational anomaly over billions of years. The process is the same process. The outcome is in a completely different category of thing. Think about what gravity has done at successively larger scales, and notice how the character of the result changes even though the mechanism does not. At the scale of a planet, gravity pulls diffuse gas and rock together until pressure and temperature build to the point where the material organizes into a sphere, heats the interior, and produces the kind of differentiated, layered, magnetically active body that can hold an atmosphere and, in at least one case, produce life. That process takes millions to tens of millions of years. At the scale of a galaxy, gravity pulls gas clouds together into stars, pulls stars into loose gravitational associations, pulls those associations into the rotating disk structure of a spiral galaxy, maintains that structure over billions of years while the galaxy slowly consumes its gas supply, and the stars it has made age and die and enrich the remaining gas with heavier elements. That process takes billions of years and is still ongoing in every galaxy we can observe. At the scale of a galaxy cluster, gravity pulls individual galaxies together into groups, pulls groups into clusters, heats the intracluster medium, the hot gas that fills the space between galaxies in a cluster, to temperatures of tens of millions of degrees, and creates the largest gravitationally bound structures in the universe. Clusters take several billion years to assemble and are still assembling. At the scale of a supercluster, and here is where the character of the result changes again, because at this scale gravity is not strong enough to hold the structure together against the expansion of space. Superclusters are not bound, they are transient. The Laniakea supercluster, the structure that contains the Milky Way, is not a stable gravitational entity. It is a region of correlated flow, a temporary configuration of galaxies all moving in the same direction that will eventually be pulled apart by the expansion of the universe. It exists now. It will not exist in any meaningful sense in a few billion years. That distinction matters more than it might seem. Everything at smaller scales, planets, solar systems, galaxies, galaxy clusters, is gravitationally bound. These structures will persist, more or less, even as the universe expands around them. The expansion of space does not undo structures that are already held together by gravity at these scales. Gravity wins locally. But at the scale of superclusters, gravity does not win. The expansion of space wins. The supercluster is a momentary pattern in the flow, and the flow is temporary, and what we are measuring when we measure the bulk flow, the drift toward the great attractor, is a pattern that is currently present and will eventually dissolve. We are, in other words, measuring something that has a lifespan. The flow is real. The flow is also going away eventually in the sense that the expansion of the universe will stretch the distances between galaxies until even the correlated motion of a supercluster is diluted into noise. In the very long run, the sky will empty not in one direction but in all directions, as galaxies recede beyond the observable horizon one by one, and the universe becomes a collection of isolated islands with no knowledge of each other. That is the long run. Right now there is still a direction. The body is useful here. unexpectedly. You are a gravitationally organized structure. Every atom in you was pulled together, first in a star, then in a planet, then through the biological processes that built the molecules that built the cells that built you. Gravity was present at every stage, not as the dominant force. Chemistry and electromagnetism did most of the work at the molecular scale. But as the organizer of the context, the thing that made stars and planets exist, which made chemistry possible, which made you possible. Gravity is in the background of everything you are, and the same gravity, scaled up by a factor of roughly 10 to the power of 50, operating on timescales of billions of years rather than billions of seconds, is what produced the large-scale structure of the universe. The filaments, the voids, the clusters, the superclusters, the bulk flow, the lean. The same law, the same constant. Just more mass and more time until the result is something that looks nothing like a falling apple and everything like the shape of the observable universe. Gravity at the wrong scale does not feel wrong. It just produces things that are hard to recognize as gravity's work, because we have calibrated our sense of what gravity does to the scales we live at, and the scales we live at are, cosmologically speaking, very small and very fast. The universe is doing the same thing your body is doing right now, being held together by the same force, organized by the same tendency of mass to seek mass. It is just doing it very slowly and very largely, and in a direction that took us until the late 20th century to notice. Laniakea. In 2014, a team led by R. Brent Tully published a paper in Nature that redrew the map. Not the map of the sky. The sky had been mapped, more or less, for centuries. The map of where we are in it. The paper used a new method, mapping not just the positions of galaxies, but the flows of galaxies, the peculiar velocities, the deviations from pure Hubble expansion, to define the boundaries of the supercluster we live inside. They called it Laniakea, Hawaiian for immeasurable heaven. The name was chosen carefully. It gestures toward the tradition of Polynesian wayfinders who navigated the Pacific by reading currents and stars and the behavior of swells, who understood the ocean not as a barrier but as a structure with directions and textures and flows that could be read if you knew how to look. The naming was a statement about method. We found this the way navigators find currents, by watching how things move. Laniakea is large, 500 million light-years across, 100,000 galaxies, a total mass equivalent to roughly 100 million billion suns. It is not the largest structure in the universe. There are filaments and walls that dwarf it. But it is ours. It is the supercluster within which the Milky Way sits, near the edge, in a quieter region, in what turns out to be a gravitational backwater relative to the main action. The main action is toward the centre, toward the gravitational basin that the flow lines converge on, toward the region the paper identified as the attractor at the heart of Laniakea, which corresponds roughly to the region of the Great Attractor, the Norma cluster, the Abell 3627 complex. Everything in Laniakea is, in a general sense, pointed at that basin, not all moving toward it at the same speed, not all going to reach it. The expansion of the universe will pull the outer regions apart before they arrive, but all carrying a component of motion in that direction. Look at the visualization that accompanied the paper. It is available, has been reproduced in many places, is worth finding if you have not seen it. It shows Laniakea as a three-dimensional structure of flow lines, each one representing the peculiar velocity of a galaxy, or group of galaxies, all of them curving toward the central attractor like rivers flowing toward a drain. The structure looks organic. It looks like a leaf, or a lung, or a watershed. A branching system of flows converging on a basin. The cosmic web, made visible not through position but through motion. The Milky Way appears in the visualization as a single point near the outer edge of one of the lobes. Small, quiet, downstream. There is something that happens when you see your address written at a very large scale. Not your street address, not your city or country or continent, your cosmic address, Milky Way, local group, Virgo Supercluster, Laniakea. Each level of that address is a structure you're inside without being able to see the walls, a container whose scale exceeds the range of any observation you could make from where you are standing. Most people, when they encounter the word supercluster, treat it as another word for very large. And it is that. But it is also a word for a specific kind of structure, a region of the universe defined not by a gravitational boundary, but by a flow boundary. Laniakea's edges are the places where the flow lines switch direction. On one side of the boundary, the peculiar velocities point inward, toward the Laniakea basin. On the other side, they point toward a different basin, a different supercluster, a different center of gravity. The boundary is a watershed divide, a continental divide, but for the motion of galaxies. We're on this side of the divide. We've always been on this side of the divide. The divide was in place long before the solar system formed. The paper's method was, in a sense, a philosophical statement about what a structure is. A structure is not defined by where its matter is. A structure is defined by how its matter moves. The flow makes the boundary. The boundary makes the supercluster. The supercluster becomes a place, not a region of sky, but a place with an inside and an outside and a direction that everything inside it is moving. Laniakea is a place. We live in it, near the edge of it, being carried very slowly toward its center, along with everything else inside its watershed. The name means immeasurable heaven. The people who named it were thinking about Polynesian navigators reading currents in a vast and apparently featureless ocean, and knowing from those currents where they were and where they were going. The current is real, the ocean is real, and the knowing, it turns out, is possible. Not easy, not fast, not available to the naked eye at any scale, but possible, with enough patience and enough data and enough willingness to watch how things move rather than just where they are, and to let the motion define the place and to name the place. Finally, something that contains both the fact of it and the difficulty of it. Immeasurable heaven. 500 million light years of it, and we are in it, near the edge, downstream. Some researchers have called this deeper signal evidence of influence from structures at the very edge of the observable universe. Concentrations of mass so far away that their light has been travelling since the early universe that the surveys we have are only beginning to reach. That the gravitational signal from them is detectable only as a faint statistical tendency in the motion of galaxies much closer to us. Faint, statistical, tendency. Those three words carry a lot of weight in this context. The further you go from the source of a gravitational signal, the weaker the signal becomes, following the same inverse square law that governs gravity at every scale. A structure at 2 billion light years produces a much smaller peculiar velocity at our location than a structure at 250 million light years of equal mass. To be detectable at all at these distances, the structure has to be very, very large. the kind of large that strains the cosmological principle, the assumption that the universe is roughly the same in all directions, because structures that large should not, according to the standard model, exist. Some surveys have reported detections of anomalously large structures at very large distances. The giant arc, a curved arrangement of galaxies roughly 9.2 billion light-years away, and about 3.3 billion light-years long, reported in 2021. The Hercules Corona Borealis Great Wall, a proposed structure over 10 billion light-years across, reported in 2013 and still debated. These structures, if real, challenge the standard assumption of homogeneity at large scales. They suggest that the universe may be lumpier at larger scales than currently accounted for than the standard model predicts. They are debated. The data is incomplete. The methods have uncertainties. This is an active area where the field has not reached consensus, and any presentation that implies otherwise is skipping over the argument. But the argument exists, and the direction it is arguing about is the same direction the flow has been pointing for 4 billion years. There is no clean terminus to this chain. That is the honest answer to the question of what is pulling. Something in the direction of the great attractor is pulling, and that something is itself being pulled toward the Shapley concentration, and the Shapley concentration may be part of a larger flow towards structures at even greater distances, and the structures at even greater distances may themselves be part of a pattern that extends to scales where the cosmological principle begins to strain. The chain does not terminate at a fixed point. The attractor is attracted. The pull that organised 4 billion years of motion in this corner of the universe is not a thing sitting still at the end of a river, but a node in a network of pulls, each one real, each one measurable in principle, and together constituting something that does not yet have a clean diagram. The sky has been emptying in one direction. The direction leads somewhere. The somewhere leads somewhere else. And the else leads possibly further still. 4 billion years of the same lean before the first fish, before the first cell with a nucleus, before oxygen accumulated in the atmosphere in quantities that would have been breathable, before the atmosphere was the atmosphere, before the oceans were the oceans, before the crust had cooled to the point where rock was stable at the surface, before all of it, the matter that would eventually become those things was already leaning, not leaning in the way a building leans, or the way a person leans against a wall, leaning in the way that an enormous volume of gas distributed unevenly across a region of space leans toward the regions of higher density around it, because higher density means more gravity, and more gravity means a net pull in a particular direction. And a net pull in a particular direction means motion. And motion, accumulated over 4 billion years, means something that has a shape and a history and a direction that has not changed since before there was anything on this planet capable of having a history. The lean is older than life. It is older than the Earth. It is, in this corner of the universe, one of the oldest continuous facts. 4 billion years is a number that appears in other contexts too. The age of the Earth is approximately 4.5 billion years. The oldest rocks on the surface are around 4 billion years old. The oldest confirmed microfossils, evidence of early cellular life, are around 3.5 billion years old, with some contested evidence pushing that back further. The heavy bombardment period, when the inner solar system was being pelted by debris left over from planetary formation, ended somewhere around 3.8 billion years ago. These numbers cluster because they belong to the same era, the early history of the solar system, when things were settling from chaos into something more organized. The lean was already in place when all of this was happening, when the first rain fell on the cooling crust, when the first organic molecules formed in tidal pools or hydrothermal vents, or wherever life first assembled itself from available chemistry, when the first light-sensitive cell turned toward the sun. All of it happening inside a galaxy that was already, quietly, moving in a direction. There is something about duration that changes the character of a fact. A fact that has been true for a week is contingent. It might change, it might be revised, it might turn out to have been a misreading. A fact that has been true for a century starts to feel structural. A fact that has been true for 1 billion years is closer to a feature of reality than a fact. And a fact that has been true for 4 billion years, that has persisted through every extinction event, every glaciation, every continental collision, every evolutionary innovation from the first cells to the first eyes to the first brain capable of asking what time it is, that is not quite a fact anymore. It is more like a condition, a property of the situation, something that was already there before there was anything to notice it, and that will still be there after the noticing stops. The lean is like that. The Milky Way formed around 10 billion years ago, from a collapsing cloud of gas in what was already a structured region of the early universe. The structure was different then. The cosmic web was younger, the filaments less defined, the voids not yet fully evacuated. But the direction toward which the local region of the universe was already organizing its flow was, even then, roughly the same direction it is organizing toward now. The specific structures, the great Attractor region, the Shapley concentration, had not yet assembled into the configurations that define them today. But the large-scale gradient in the density field was already there, already producing a net gravitational pull in a particular direction, already set in the terms of what would become, over billions of years, the bulk flow that the Seven Samurai measured. The lean goes back further than the Milky Way, further than the solar system, back to the earlier structure formation when quantum fluctuations in the density of the early universe, fluctuations so small they would have been invisible to any measurement technology imaginable, were amplified by gravity over hundreds of millions of years into the first filaments and voids and concentrations that would eventually become the cosmic web we inhabit now. The fluctuations were laid down in the first fraction of a second after the Big Bang. By the time the universe was a few 100 million years old, they had grown into the seeds of large-scale structure. By 1 billion years, the first galaxies were forming in the densest regions. By 4 billion years, the structure was recognizable as a web. By 10 billion years, galaxies like the Milky Way were assembling. And throughout all of it, from the moment the density fluctuations first created a gradient in one particular direction, in this particular region of the universe, the lean was present, not announced, not dramatic, just there, built into the geometry of the matter distribution, doing what gravity does, which is pull, incrementally, patiently, without interruption, toward the nearest concentration of mass. 4 billion years of the same lean. The Earth formed. The lean continued. Life appeared. The lean continued. Cells developed nuclei. The lean continued. Fish crawled onto land. The lean continued. Forests appeared and burned and appeared again. The lean continued. Something looked up at the night sky for the first time and felt something. The lean continued. The lean is continuing right now. There is a word in geology, unconformity. It describes a gap in the rock record, a surface where two layers of rock meet, but the layers are not continuous in time, where something happened between the deposition of one and the deposition of the other that left no record, or whose record was eroded away. An unconformity is a missing chapter, millions or hundreds of millions of years gone. The rocks above the surface are younger, the rocks below are older, and the contact between them is a gap that the geological record simply cannot fill. The Lean has no unconformities. There was no pause, no period during which the matter in this region of the universe stopped drifting toward the great attractor and then resumed. No gap in the flow record. 4 billion years, continuous. The Earth was doing one thing while all of that was happening. Forming, cooling, generating life, evolving that life through successive crises, eventually producing organisms capable of measuring the motion of galaxies. And the whole time, without pause, the galaxy those organisms lived in was falling towards something, quietly, in a direction, the same direction it has always been falling.